Hello class, this is Mr. Hart, and in this video I want to talk about something that I have received many comments asking that I make a video on this, and this is about quantum computing. Now I did a video series on quantum mechanics, but quantum computing is one of those new and interesting ideas that has just started to become something that's actually viable. And a lot of people are hearing about it and want to learn more about it, and so I want to make this video giving you a little bit of understanding of what quantum computing means and how it could potentially change everything with computation. And I like it a lot too because my degree is in computer science, so I'm excited to tell you a little bit more. So, for example, with all the hype, you've probably heard about companies like IBM and Google buying quantum computers. Right now, when I'm making this video, the largest quantum computer is 72 qubits, and it's owned by Google, and it's called the Bristlecone. I don't know why they called it that, but that is what it is called. And they're really funky looking computers that have all sorts of switches everywhere, and they're often kind of dangling in chambers. I don't know if that's a design choice that's necessary or if it just looks cool, but either way, these are spectacular machines, and they're starting to become more and more powerful and have more and more qubits. And so, along with this video, I'm going to attach another video that gives a pretty good job of explaining how a quantum computer works. But I want to talk more about why quantum computing is such a big deal and what it would mean. So in addition to watching this video and understanding how it works, let's talk about how this is revolutionary from how regular computers work. So if you have a regular computer and machine, not a quantum machine, but a regular machine, it can be your phone, your desktop, your laptop, etc. Okay, it runs on binary numbers, and those binary numbers have to be fed through one at a time. Now, this can be done really, really fast, but it still has to be one at a time. It's still a limitation. So, for example, the new i7s and i9s and these other CPUs can do around 3 to 4 gigahertz per second. Okay, and they may have quad-core or octa-core processors, which means they can do 4 times or 8 times as much as what's listed. But even still, with a 3.2 gigahertz processor, you're looking at about 3.2 billion calculations or possibilities every second. Now, the reason why is because you are feeding in binary numbers, or what's called a string of bits, basically just a little list of bits, and it will just be ones and zeros all the way through. But each 1 and 0 has to be fed through one at a time. And again, 3.2 billion of them can go through at a time, but they have to be fed through one at a time. Now, what makes quantum computing so cool is that this limitation of one at a time goes away. So in a quantum computer, you can do a whole bunch of things simultaneously. Now, we have quad-core and octa-core and dual-core processors, which multiplies things by 2 or 4 or 8, right? We're doing a lot of things in parallel, which is good. But with a quantum computer, you can do all of your calculations simultaneously because qubits, not just regular bits, but qubits, quantum bits, can exist in multiple states at the same time. Now, if you have watched my other videos, we talk a lot about this idea that in quantum mechanics, everything's talked about by probabilities and wave functions and states. And so these things can have different probabilities and states in different spots. And a qubit can be a 0 and a 1 at the same time. You can have probabilities in both. So what that means is that a 72 qubit quantum computer that Google has, for example, could calculate 2 to the 72 things about every microsecond. That is 4 octillion calculations every second. That is insane to think about compared to our billions of things. We're looking at octillions of calculations every second. Okay. Now, there's still a lot of things to work out. Even though you can do this many things at a time, being able to measure appropriately and correctly all those things at the same time and accounting for probabilities and for error and things like that are things that still need to be worked out. But this could potentially just be crazy powerful with the number of computations you could do. So I want to ask you this. Why is this useful? Okay. I mean, your computer is probably already pretty fast. We can run videos and games and all sorts of calculations on them. But why would we want a quantum computer? Well, it's unlikely that you'll see consumers have quantum computers anytime soon. Your phone's not going to have a quantum chip in it anytime soon. But for research and for companies and for development, quantum computers can be super useful. So for example, think about encryption, okay? Keeping things secure on the internet. Now, right now, you can't break encryption codes for logging into a bank, for example, or anything online without knowing the password, because you can't try every single password at the same time. Unless you happen to have a quantum computer and you can try every single password at the same time and try every single factorization of the encryption code at the same time. So quantum computers would actually break our current encryption systems. But the good news is that they would make new encryption systems that are even more powerful. If a regular computer can't break an encryption system, then a regular computer couldn't break a quantum encryption system by any means. Think about all the different ways that could factor and make secret codes and all these things with every possibility tried at the same time. You can make a new scheme for encryption that could be even more powerful than our current one. With quantum computers, you could do things like rendering for movies and video games. You may not know this, but when you have a 3D movie like Pixar makes or Disney makes, they spend hours and hours of time on the computer making the scenes, but they also have to take the time to render the scenes in the final video, meaning it has to figure out where all the geometry lies and how all the lighting will look and where everything will go and how the color will look. And that process can take a lot of time. There are actually whole server farms that these companies own that just render scene after scene after scene making the movie. Well, if you have a quantum computer, you could potentially make all those scenes in an instant because you could calculate where all the lighting goes and all the colors and configurations are on that scene. And so we could render movies instantly without having to wait for the program to churn and churn and churn to make these movies. So movies could be made faster and more effectively and made better. There's all sorts of research applications of problems we've said in the past, like, oh, we can't do that. It just would take forever to run. Well, with a quantum computer, that's no longer an issue. So it increased research and development and all sorts of amazing things. You may have heard of deep learning and AI. Deep learning takes a long time to train and to teach these machines how to recognize objects. Well, with a quantum computer, you could potentially train those things instantly because they could try every possibility and then know what the correct answer is. And so we could train deep networks in an instant. So there's just endless possibilities to what quantum computers could do. So I'm really excited for what things they could unlock in the future. So what I want to do for this last little bit is show you how a quantum computer could actually be programmed and show you a site where you can actually practice programming a quantum computer. It's really cool. So the site we want to go to is called qcengine.com, or another reference is machinelevel.com/QC. So if you just open up your browser and go to qcengine.com, or quantum computing engine, it'll take you to a site that looks like this. And I prefer to use the toolbar down here. Sorry, here it is. The QC Engine Workbench. And it gives you code that looks like this. Now, I won't have the time to show you all of programming and quantum programming in one movie, but I want to give you a hint and a taste of what this looks like. So I'm going to give you a little bit of code, and then we're going to write some code together. So here's a little bit of code I want you to know. So here is the code that I will give to you, and this is also in the worksheet for this lesson. But what it basically does is it allows us to set up the machine. Now, each line is its own line of code, and every line needs to be ended with a semicolon. That's just a programming convention. If you're wondering, it's based very similar to JavaScript. And what this is going to do is if we run this code, it gives us basically a blank slate of numbers to work with. Okay? So we have reset the system, which basically just means start from scratch. We're going to make a set of numbers, which we'll call numbers. And we're going to do some computations on those numbers, and we're going to call them answers. And you may know from other computing classes that you can represent the number of bits that you want to represent, and that's always a power of 2. So if I give it 3, that means I have 2 to the 3 possibilities, or 8 spots. So we're going to work with numbers up to 8. And our calculations will allow values up to 2 to the 6th, which is, if we make this bigger, 64 values. So if we need to make computations that go bigger or larger, we need to change these numbers. But for our purposes, this will do what we need it to do. And then we basically start with the number 0 on both the answers and the numbers. So this is just some code to initialize the system. Okay, then the thing that's going to be really useful is what's called the Hadamard. Okay, and so it's qc.hadamard like this. And when we run this, what it's going to do is it's going to put all possible numbers and all possible answers in superposition with each other, meaning that they're all equally likely. Now, this is basically just setting up the computation so we can say, let's do all these things at the same time. I want to consider every possible input, and I want to consider every possible output. Okay, they're all equally probability. The size of these circles shows the amount of probability we have assigned to it. Sorry, just making a quick correction. I realized I need to do numbers.hadamard. We only want to put the numbers in superposition. We only want the answers to be at 0. So now all the numbers are equally probable, and now we're going to see how that affects the answers. So now we can do things like answers.add numbers. And what this will do when we run it is it considers all the numbers and it adds it to the output. So all the output answers are just the numbers we started with. So then we can do things like answers.add 1. And that will shift all the numbers by 1. We can do things like answers.add squared numbers. Sorry, I just needed to make sure we had a capital S there. And then you'll see that we get 1, 3, 7, 13, 21, 31, 43, 57. If you look, that's each number plus 1 squared. Okay? And so we could add this by 5, and now we're shifting those by 5. And it shows us the most probable quantum states. And those most probable states are the solution to this calculation for each number that we considered. And so it's just a very powerful idea that we can consider all the numbers at the same time and then find the calculation that we're doing for all of them at the same time. So again, there's a lot of new code you could do, but for now I just want you to understand how to add the numbers, add their squared values, and then add some offset. So you could do calculations of addition on all these numbers at the same time. Now just imagine if you did that with 2 to the 72 values at the same time. And that is amazingly powerful. So there you go. That's quantum computing. I invite you to play around a little bit with this program. It's really cool to see and visualize how the probabilities are moving around. But I hope that made sense. I hope you found this interesting. And thank you for watching.